Okay, this is actually first lecture in chapter 5 of the book by Norman Nice, and the title of that chapter is Reduction of Multiple Subsystems, as you can see. And let me give a motivation for this chapter. Uh, Suppose that we have, as an example, the electromechanical system that we have considered, which is composed of a DC motor, uh, driving a mechanical load of inertia J with friction in the environment, this is called B. If I apply an input EI to the circuit, which is composed of a resistance and an inductance, this will be corresponding to the winding of the motor. That will produce a current I and a back EMF, we call it EB. Accordingly, the current will introduce a torque that will result in rotation of the mechanical system. Let's say the rotational angle is theta. So we can write the equation of this system. So we'll have Kirchhoff voltage law to the electrical loop. So EI minus EB, that would be equal to I times R plus L di by dt. And as I said, that will result in a torque, which is some constant kt times the current. And that torque will result in rotation. So we apply Newton's law. So we'll have G theta double dot equals T, the driving torque, minus the friction torque, B times theta dot. Finally, the back EMF is some constant, call it Kb, times theta dot. So if we apply Laplace transform to these equations, we will get EI minus EB divided by R plus SL. So that would be the Laplace transform of this right hand side of the equation. That should be equal to the current I. The second equation is just an algebraic equation, so torque will be equal to K times I. Finally, we have here from the mechanical equation J s squared plus Bs times theta equals T, and the last equation would be E equals K times S theta. So now I have represented all equations in the frequency domain. I can have a block diagram to represent that. So the first equation would be with input EI minus the back EMF EB, that multiplied by 1 over R plus SL, that gives the current, multiplied by K, that will give the torque, and if I divide that by 1 over J s squared plus Bs, that will give me theta. If I'll multiply that by Kb times S, that will give the back EMF. So this is a block diagram that represents the subsystems. Here we have, as I mentioned, electrical and mechanical subsystems. So this is the block diagram. The question is how to find an overall relation that relates theta, the output, to the input. So how to find the transfer function from the block diagram. Or another question would be how to find the state space model representation that relates the different signals to the input and the output. So these two questions are answered through this chapter. So what is the outline of the chapter? First, we'll talk about block diagrams, and this is the topic of this lecture. Then we'll see another graphical representation of the modeling equation, and that's called the signal flow graph. It will have the same purpose, to find the overall transfer function between the input and the output, or to find the state space modeling that relates the different state variables to the input and the output. And finally, in this chapter, we'll see different possibilities of representing the same system by different representations in the state space, and that means choosing different state variables, as we have mentioned during the lecture before. Now, what is the objective? Again, the objective is to present the modeling equations graphically, either using the signal flow graph or using the block diagrams. So this is a way of representing the modeling equation graphically. And the ultimate goal of that is to find the transfer function or the state space models. Afterwards, of course, you can use that for either analysis or design. So in order to start with block diagrams, we have to see the different components of a block diagram. So the basic component is the signal. And as you know, the signal would be represented by its symbol and direction. Also, we have systems and are represented by boxes where the gain could be just a pure gain or a transfer function G. And typically, any system has input and output. So the direction of the arrow determines the direction of the input. So this is an input, R is an input because of its arrow direction, and C is an output because it's coming out of the system. And we know that the relation between the output and input is that C equals G times R. So this is what we have here. Another possibility that we could encounter in block diagrams is the summer. So you have signals R1, R2, and R3 coming here positive, positive, and negative. So the output of the summer would be just the summation of the positive one minus the negative one. So this is another possibility in block diagrams. And finally, we have what's called pick-off points. And this is the same signal, but going through different routes. So we have here R, and R, the same signal, but it will be branching to different directions, as we are going to see. Blocks could be connected in different ways, could be in series like that. We call that series connection or cascaded connection. And we can combine two series blocks into just one block, as we can see here, and that would be the product. The proof is very simple, because x2 here is equal to g1 times x1, and x3 is just g2 times x2. So if you substitute for x2 by g1 x1, that will give you g1 g2 times x1. So that would result in x3 equal g1 g2 times x1, as we have here. So now the parallel blocks, this is a combination when you have the same signal R entering into three different, or maybe more or less, transfer functions. So coming out to a summer, so we can replace this parallel combination by just the summation of the transfer function. So as you can see here, the three branches here are replaced by plus or minus g1, plus or minus g2, plus or minus g3, depending of course on the signs that appear at the summing junction. So again, this is another possible way to reduce the parallel blocks. The next configuration, this is called the negative feedback or positive feedback combination. Now let us first define this direction, the direction which is coming from the input towards the output, to be called feed forward, and the direction that comes from the output back to the input as the feedback direction. Now, based on the sign here, this sign, if it is negative, like this signal, we call that negative feedback. So this is negative feedback. However, if it is positive, we call that positive feedback. So that's how we define the configuration. So we say that this is a negative or positive feedback because there is a signal coming from the output towards the input direction. Positive or negative based on the what appears as a sign. Now we are going to show the relation between the output and input in case you have feedback, and you can see here in case of negative feedback, the sign that appears down here is positive, so it's opposite to the type of feedback. While if it is positive, then the sign that appears here is negative. So let us try to prove that. I'm going to consider a negative feedback loop. That means that the feedback signal is negative here. We have in the forward direction G. This is the input R. This is the output C. Here you have the feedback transfer function H. And now our purpose is to find the relation between output and input. Now let me call this signal E. So we can write E equals R minus this signal. What is this signal? If you have here C coming into H, then the result here would be H times C. So it is R minus H C. Now what is C? You have here a signal E coming into G, so the output will be equal to G times E. So we can write C equals G times E. I'm going to substitute for C in here from this relation G times E. So I get E equals R minus H G E. If I move that to the left hand side, I will have 1 plus H G times E equals R. That means E equals R over 1 plus GH. However, we know that C is equal to G times E, so we can write C equals G over 1 plus GH times R, and this is the final relation that we wanted to find. You can see here that you have a negative feedback, and the sign that appears here is positive. I'd like you to repeat this derivation, assuming the signal here to be positive, and you will notice that the result will be a negative sign in the denominator here. So do it yourself. Now, possibilities that could arise in dealing with block diagrams is that sometimes you could have a combination like that, which is a summing point and a transfer function, and for some reason, to do simplification, you would like to move the summing point to be behind the block, so you will move it to this direction. So how would you do that? The main criteria is to keep the output signal unchanged. What is the output signal here? The output signal is x3, and that's equal to g times x1 plus or minus x2. So when we move g, as we can see here, we must keep x3 unchanged. Now, according to the new situation, we have here g times x1, and what we should have here is g x1 plus or minus g x2. Now, this is x2 entering the system. In order to get this second term correctly, as it appears here, then x2 has to be multiplied by g, as we can see here. So we get the correct answer. So the criteria here is that when you move a block or a transfer function around a summing point, you have to make sure that the output signal in the original configuration remains unchanged. Now here, moving the summing point ahead of a block. So we have, this is the original system, and would like to move the summing point ahead of the block, as we have done here. So again, what's to be kept unchanged is equal to gx1 plus or minus x2. That has to remain unchanged after changing the location of the summing point. So if I move g, as you can see here, what you get? You get g times x1, so that's fine. But x2 has to appear in the result as without any thing multiplied by it. So that's why I have to multiply here by 1 over g, because this signal here would be x2 over g. When it goes through the summer and then multiplied by g, this g will cancel out with the g in the denominator, and the result will be x2 as required. So that will give me again plus or minus x2 as in the original system. So this is the idea. Keep the output signals unchanged after you move a block around the summing point. Similarly, we can move the pickoff point around a block, around a transfer function. So suppose we are moving a pickoff point behind a block, so we move it in here. So again, what is the output? The output is x1 and it's also x2. So we have to keep x1 and x2 unchanged. So if I move the pickoff point to be here, x2 will remain unchanged because still it is x1 times g, like in here. So that's okay. However, we have to keep the signal here to be x1. But if you take the pickoff point from this from x2, then in order to keep it as x1, you have to divide here by g. So that's what I did here. So you still have x1 unchanged as in here. Moving a pickoff point ahead of a block, so this point is to be moved here. Again, what you have here as outputs would be x2. So if I move the point here, the signal in this direction remains to be x2, which is gx1. This is gx1, so that's correct. However, this signal has to remain as x2 g times x1. so I have to multiply here by g in order to keep x2 unchanged. So these are the basic ideas that we have to follow. However, notice that in the possibilities of moving pickoff point and blocks or summing point and blocks, we haven't actually mentioned moving or interchanging a pickoff point and a summing point. That is not allowed. That will result in wrong results. So don't try to do this. I will give you an example to illustrate. For example, if you have this block diagram and I ask you to find the corresponding input-output relation. Now, you can see that you have here a feedback loop. We know the expression for that. We have here another feedback loop, and we have a feedback like that. However, the problem is this point. This point in the middle of the loop. So if we reduce this positive feedback by a single block, this point will disappear. If it disappears and we don't make sure that we still have the signal here entering the summing point unchanged, then we get wrong answers. So what we do, we have two possibilities, either to move this point to the right like this, or to move it to the left. If we move it to the left, we are stuck, because here you have a summing point and pickoff point after changing, and as I mentioned a few minutes ago, this is not allowed. So what we should do actually is to move the pickoff point to the right. In that case, in order to keep the signal unchanged, we have since the new signal will be multiplied by G4, we have to divide by G4, and that's what happened here. We moved this point like here, and we divided by G4, so the signal here will remain unchanged as it was before the adjustment. Now, once we do that, this is a simple block diagram, because we just have multiples of feedback loops that we can reduce. So we have, this is a loop, this is another loop, and this is a third loop. So we can reduce them successively, and we can get the final result. So that's what I did here. This is the first loop, which is positive feedback. That's why you have a negative sign here. You multiply it by G2 because those are in series, and then you can reduce those into just one block. That's what is happening here. So this is a reduction of that. And then you multiply by G1, and you have the final negative feedback loop, this one. So you will get the result of Y over R. So this is how you would reduce this block diagram.